China's artificial sun achieves historic milestone, 1,056 seconds of continuous nuclear fusion ignition. Date, January 25, 2025. Overview. China's experimental advanced superconducting Tokamak East, often referred to as the artificial sun, has reached a groundbreaking milestone in nuclear fusion research by maintaining high-confinement plasma operation for an astonishing 1,066 seconds. This achievement, reported on January 20, 2025 by the Institute of Plasma Physics under the Chinese Academy of Sciences, significantly surpasses the previous record of 403 seconds set in 2023. This progress is pivotal as it marks a substantial step towards the development of future fusion reactors that can produce continuous and clean energy. Key highlights. 1. Record-breaking achievement. The 1,066-second plasma operation not only sets a new world record but also illustrates significant advancements in sustaining high-temperature plasma, which is essential for the self-sustaining plasma circulation necessary for commercial fusion reactors. 2. Technological innovations. East is recognized as the world's first fully superconducting tokamak featuring a non-circular cross-section and actively water-cooled plasma-facing components. These innovations provide greater flexibility for experimental configurations compared to traditional reactors like ITER, enhancing research capabilities. 3. Importance of fusion energy. Fusion energy, which mimics the nuclear reactions occurring in the Sun, is celebrated for its potential as a clean and virtually limitless power source. Unlike fossil fuels, fusion generates minimal waste, producing only helium as a byproduct. The hydrogen isotopes used in fusion are abundant, making it a promising alternative for future global energy needs. 4. Global collaboration. China's involvement in the International Thermonuclear Experimental Reactor ITER project is acknowledged, where it contributes approximately 9% of the construction and operational efforts. The advancements made by East are expected to inform and bolster the development of ITER and other experimental reactors, such as China's forthcoming fusion engineering test reactor ITER. 5. Future challenges. Despite this significant progress, challenges remain in achieving practical nuclear fusion. Researchers must overcome obstacles such as maintaining plasma stability at temperatures exceeding 100 million degrees Celsius and ensuring long-term operational stability. High efficiency is critical for achieving consistent energy output in future reactors. Timeline of events. 2006 – Launch of East, serving as an open test platform for global fusion research. 2022 – East maintained high-temperature plasma for 102 seconds. 2023 – East set a previous record of 403 seconds of continuous plasma operation. January 20, 2025 – East broke its own record by achieving 1,066 seconds of continuous nuclear fusion ignition. Conclusion. The recent achievement by China's artificial sun not only sets a new benchmark in fusion research but also emphasizes the significance of international collaboration in tackling global energy challenges. Continued advancements in this field may eventually lead to the realization of fusion energy as a viable and sustainable power source. This landmark achievement showcases the importance of ongoing innovation in nuclear fusion technology, paving the way for a cleaner energy future. Sources. 1. Innovation News Networks / www.innovationnewsnetwork.com/ China's artificial sun achieves fusion milestone 1066-second plasma / 54789/. 2. Live Science Apps / www.livescience.com/planet Earth / nuclear energy / China's artificial sun shatters nuclear fusion record by generating steady loop of plasma for 1000 seconds. 3. Chinese Academy of Science / english.cas.cn/newsroom/multimedia news /202501/T20250122899195.html The recent achievement of China's experimental advanced superconducting Tokamak East, which maintained high-confinement plasma operation for 1066 seconds, marks a significant milestone in nuclear fusion research. This breakthrough is not only a remarkable technical feat, but it also presents several counterintuitive insights about the current state and future of fusion energy. 1. Misconceptions about fusion readiness. Many people might assume that with the recent advancements in fusion technology we are on the brink of having practical fusion power plants. However, despite achieving a record duration of plasma confinement, experts caution that practical fusion energy generation remains a distant goal. The reality is that sustaining plasma at the required temperatures and achieving a self-sustaining reaction where the fusion process generates more energy than it consumes are still significant hurdles. This counters the expectation that these milestones directly translate into imminent energy solutions. 2. Focus on duration over efficiency. The record of 1066 seconds might suggest a breakthrough in efficiency. However, East's operation still consumes more energy than it produces. This is counterintuitive, as one might think that longer plasma confinement would automatically lead to a more energy-efficient process. Instead, the emphasis currently is on the stability and duration of plasma confinement, which are essential for future reactors even if they do not yet signal a net positive energy output. 3. The nature of fusion fuel. There is a common belief that fusion energy is a universally applicable solution due to its reliance on abundant fuel sources like hydrogen isotopes. However, the reality is that while deuterium is indeed plentiful in seawater, tritium is not naturally abundant and must be bred from lithium, which introduces additional complexities in reactor design and operation. This nuance may not be widely understood, leading to an oversimplified view of fusion as a straightforward energy solution. For international collaboration dynamics, while the narrative often highlights national achievements in fusion research, it overlooks the collaborative nature of the field. China's contributions to the International Thermonuclear Experimental Reactor ITER project, in which it holds around 9% of the effort, illustrate that breakthroughs in fusion are not solely the result of national programs. This interdependence suggests that advancements made in one country's reactor can significantly benefit global efforts, contrary to the perception of isolated national successes. 5. The role of smaller reactors. The East's design as a smaller Tokamak compared to ITER may suggest that larger reactors are necessarily more advanced or capable of achieving fusion first. However, East's unique features, such as its fully superconducting magnets and flexible operational modes, allow it to experiment in ways that larger reactors cannot. This indicates that smaller or differently designed fusion reactors can play a critical role in advancing the technology, challenging the notion that size equates to capability. 6. Public perception of nuclear energy. The term artificial sun evokes a sense of optimism and safety around nuclear energy, implying a clean and limitless source of power. Yet the complexities and dangers associated with nuclear fusion, such as the need for extreme conditions and potential radiation hazards, are often downplayed. This discrepancy between public perception and the technical realities of fusion energy reflects a broader misunderstanding of nuclear technologies. 7. Long-term vision versus short-term reality. The timeline of fusion research often emphasizes the potential for fusion to solve energy crises in the coming decades. Yet many experts argue that this timeline could extend much longer due to the technical challenges that remain. The expectation that fusion will soon become a mainstream energy source is countered by the reality that decades of research have yet to yield a commercially viable reactor, emphasizing the need for patience and continued investment in the field. In summary, while China's achievement with East represents a significant step forward in fusion research, it also reveals several counterintuitive insights regarding the nature of fusion energy, the challenges it faces, and the broader implications of these advancements. Understanding these nuances is crucial for setting realistic expectations about the future of fusion as a sustainable energy source. In the report regarding China's experimental advanced superconducting Tokamak East achieving 1066 seconds of continuous nuclear fusion ignition, several key points may be overlooked, yet they carry significant implications for the future of energy technology and international collaboration in scientific research. 1. Technological innovations of East. While many reports mention the advanced features of East, such as its fully superconducting magnets and actively water-cooled plasma-facing components, the broader implications of these technological innovations are often underappreciated. The unique design of East, including its non-circular cross-section, allows for more flexible experimental configurations compared to traditional tokamaks. This flexibility could lead to breakthroughs in plasma confinement and stability, which are critical for achieving practical fusion energy. Understanding the significance of these technological advancements is essential, as they could inform the design of future reactors worldwide, enhancing global efforts in fusion research. 2. The role of hydrogen isotopes. The potential of fusion energy to utilize hydrogen isotopes, particularly deuterium and tritium, is frequently mentioned but not deeply explored. These isotopes are not only abundant but also widely available from seawater and lithium, making fusion an attractive long-term solution for energy sustainability. The significance of this point lies in the fact that as fossil fuel reserves dwindle and the world grapples with climate change, the abundance of fusion fuel could provide a stable and secure energy future, fundamentally altering energy economics and security on a global scale. 3. International collaboration and its future impact. While the report highlights China's contributions to the ITER project and global fusion efforts, the nuances of international collaboration often go unacknowledged. The advancements achieved by East are part of a broader collaborative framework that involves multiple countries working together to solve one of humanity's most pressing challenges: sustainable energy. This collaboration not only fosters technological advancements but also builds diplomatic ties and shared goals among nations. In an era marked by geopolitical tensions, the success of such collaborative scientific endeavors can serve as a model for other fields, emphasizing the importance of unity in tackling global issues. 4. Challenges beyond the record. Although the achievement of 1066 seconds is groundbreaking, the challenges that remain in the field of nuclear fusion are often downplayed. The fact that sustaining plasma at temperatures exceeding 100 million degrees Celsius is still a formidable barrier is crucial to acknowledge. This highlights the complexity of fusion research and the need for continued investment and innovation. The report mentions the necessity for high efficiency and long-term stability in future reactors, but the specific engineering and scientific challenges that need addressing, such as plasma turbulence, magnetic field stability, and energy input-output ratios, are critical areas that require focused research and development. 5. Fusion's role in space exploration. The report briefly touches on the potential of fusion energy to revolutionize space exploration but does not elaborate on this transformative potential. If fusion technology can be developed for practical energy generation, it could enable long-duration space missions by providing a lightweight and efficient power source. This aspect of fusion energy could have profound implications for humanity's future in space, including potential missions to Mars or beyond where conventional energy sources are impractical. 6. Implications for climate change mitigation. The potential of fusion energy to provide a clean, virtually limitless power source is mentioned, but its implications for climate change mitigation are often not fully explored. Fusion energy could drastically reduce reliance on fossil fuels, thereby lowering greenhouse gas emissions and helping to meet international climate targets. The significance of this potential is amplified by the urgency of addressing climate change, thus the progress of fusion research could directly impact global efforts to combat this crisis. In summary, while the report on East's achievement is momentous, understanding the broader implications of this breakthrough, technological innovations, the role of hydrogen isotopes, international collaboration, ongoing challenges, the impact on space exploration, and the potential for climate change mitigation, offers a more nuanced view of the future of fusion energy. These facets underscore the significance of continued investment, research, and international cooperation in realizing the promise of fusion as a sustainable energy source. 1. Record-breaking achievement: the achievement of sustaining high-confinement plasma operation for 1.066 seconds by China's experimental advanced superconducting Tokamak East represents a significant advancement in nuclear fusion research. This milestone indicates progress towards realizing practical fusion energy, marking a crucial step towards developing reactors that can generate continuous and clean energy. The ability to maintain stable operation over such an extended period is essential for achieving self-sustaining plasma circulation, which is critical for commercial fusion reactors. 2. Technological advancements: East is notable for being the world's first fully superconducting tokamak, incorporating unique features such as a non-circular cross-section and actively water-cooled plasma-facing components. These innovations enable more flexible experimental configurations than traditional reactors, positioning East as a critical player in fusion research. The advancements in East's heating system, which now generates double its previous power output, demonstrate the ongoing technological progress necessary for sustaining high-temperature plasma operations. 3. Significance of fusion energy: fusion energy holds the promise of being a clean and virtually limitless power source, producing only helium as a byproduct and avoiding the greenhouse gas emissions associated with fossil fuels. The hydrogen isotopes used in fusion are abundant and widely available, making fusion an attractive energy solution for addressing future global energy demands. The potential for fusion energy extends beyond Earth, potentially revolutionizing space exploration by providing efficient power for interstellar travel, thus highlighting its transformative impact on both terrestrial and extraterrestrial energy applications. 4. Global context and collaboration: China's contributions to the International Thermonuclear Experimental Reactor ITER project, where it plays a significant role in construction and operational efforts, underscore the importance of international collaboration in fusion research. The advancements achieved by East are expected to inform and support the development of ITER and other experimental reactors, such as China's upcoming fusion engineering test reactor ITER. This collaborative spirit is essential for overcoming the complex challenges that remain in achieving practical nuclear fusion, emphasizing the necessity of shared knowledge and resources in the global pursuit of fusion energy. 1. The Manhattan Project, 1942 to 1946. The Manhattan Project was a research and development project during World War II that produced the first nuclear weapons. It involved collaboration between scientists from the United States, the United Kingdom, and Canada, and was driven by the fear that Nazi Germany would develop atomic bombs first. The project led to the creation of two types of bombs, one using uranium-235 and the other using plutonium-239. The successful tests culminated in the bombings of Hiroshima and Nagasaki in August 1945, which played a significant role in ending the war. The Manhattan Project marked a monumental leap in nuclear physics and had profound implications for international relations, warfare, and energy policies in the subsequent decades. 2. The ITER Project, International Thermonuclear Experimental Reactor. The ITER project is an international nuclear fusion research and engineering project which aims to demonstrate the feasibility of fusion as a large-scale and carbon-free source of energy. The project, which began in the late 1980s, involves collaboration between 35 nations including China, the European Union, India, Japan, Korea, Russia, and the United States. The ITER reactor, under construction in France, aims to produce 10 times more energy than it consumes through nuclear fusion, specifically utilizing deuterium and tritium as fuel. By simulating the processes that power the Sun, ITER represents a significant step toward renewable energy and has the potential to revolutionize the energy landscape by providing a sustainable and virtually limitless power source. 3. The Tokamak Research, 1950s present. The tokamak is a device designed to confine plasma using magnetic fields in order to facilitate nuclear fusion. Developed in the Soviet Union in the 1950s, it has become the most researched and developed fusion reactor design globally. Many countries including the United States, China and Russia have built their own tokamaks to explore the potentials of nuclear fusion. The tokamak design is noted for its ability to maintain the necessary conditions for fusion such as high temperature and pressure by using powerful magnetic fields. As seen in China's EAST project, advancements in tokamak technology continue to push the boundaries of what is possible in fusion research, demonstrating the device's critical role in the quest for sustainable energy. Future outlook: predictions for China's artificial sun and nuclear fusion energy. As the world shifts towards sustainable energy sources, China's experimental advanced superconducting Tokamak East, often referred to as the artificial sun, has achieved a significant milestone by maintaining continuous nuclear fusion ignition for 1066 seconds. This achievement not only marks a watershed moment in fusion research but also sets the stage for what we can expect in the coming years regarding nuclear fusion technology and its potential impact on global energy systems. 1. Advancements in fusion technology. The progress demonstrated by EAST indicates that we are on the cusp of significant advancements in nuclear fusion technology. Over the next decade, we can anticipate a series of breakthroughs that will enhance the efficiency and stability of fusion reactors. Higher temperature and pressure operations. With EAST's successful operation at high temperatures, future reactors are likely to achieve even greater temperatures and plasma confinement times. Research will focus on innovations that allow for efficient heating and confinement, leading to extended operational periods. Development of next-generation reactors, following EAST. The upcoming Fusion Engineering Test Reactor (ITER) and the International Thermonuclear Experimental Reactor (ITER) are expected to leverage the data and insights gained from current experiments. These reactors will strive toward achieving self-sustaining fusion and will likely begin operations in the late 2030s. 2. Commercialization of fusion energy. The journey from experimental breakthroughs to commercial fusion energy generation will be gradual but promising. First commercial plants by 2050. Experts predict that the first commercial fusion energy plants could become operational by 2050. These plants would provide a clean, virtually limitless energy source, significantly contributing to the global energy mix and aiding in the transition away from fossil fuels. Economic viability. As technology matures and research continues, the costs associated with fusion energy production are expected to decrease. By the mid-21st century, fusion energy could become economically competitive with traditional energy sources, driving a new era of energy independence. 3. Global energy landscape transformation. The implications of successful nuclear fusion technology will reverberate across the global energy landscape. Reduction in greenhouse gas emissions. Fusion energy producing only helium as a byproduct and generating no greenhouse gases will play a crucial role in mitigating climate change. A transition to fusion energy could significantly reduce the world's reliance on carbon-intensive energy sources. Energy security and accessibility. Fusion energy's abundance and potential for localized energy production will enhance energy security and accessibility. Countries, especially developing ones, could harness fusion technology to meet their energy needs without relying on imported fossil fuels. 4. International collaboration and research integration. The global pursuit of fusion energy will necessitate increased collaboration among nations and research institutions. Strengthening global partnerships. Initiatives like ITER exemplify the collaborative spirit required for successful fusion research. As more countries, including China, the US and European nations, contribute expertise and resources, the pace of innovation in fusion technology will accelerate. Shared research platforms. The establishment of international research platforms focused on fusion technology will facilitate knowledge sharing and expedite the development of practical applications benefiting all participating nations. 5. Addressing challenges. Despite the promise of fusion energy, several challenges remain that researchers will need to overcome. Sustaining long-term plasma stability. achieving continuous plasma operation without disruptions at extreme conditions is essential for commercial viability. Ongoing research will need to address material science challenges and develop advanced control systems. Public perception and policy support, gaining public acceptance and ensuring supportive policies will be crucial for the future of nuclear fusion. Educating the public on the safety and environmental benefits of fusion energy will be vital as projects advance. Conclusion. The historic achievement of China's artificial sun in sustaining nuclear fusion ignition for over 1,000 seconds is a pivotal milestone that signals a promising future for fusion energy. With continued advancements in technology, increased international collaboration, and a focus on overcoming existing challenges, fusion energy could emerge as a cornerstone of a sustainable and clean global energy landscape by the middle of the 21st century. The potential for near-limitless clean energy holds significant promise for addressing the pressing energy demands and environmental challenges faced by humanity.